Hello, I'm Dr. Ajay Sharma, Department of Electronics and Communication Engineering, James Engineering Management Technical Campus, Greater Noida. The subject that I teach in this semester is digital communication, and the topic that I discussed in this video lecture is random process or stochastic process, stationary and non-stationary process, WSS, wide sense stationary, SSS, strict sense stationary process, ergodicity. First of all, random process are also called as stochastic process, right? So in probability theory, a stochastic or random process is a mathematical object usually defined as a family of random variables, right? There are some examples, such as the growth of bacterial population. It's a random process. An electrical current fluctuating due to thermal noise, so movement of electrons, or the movement of gas molecules. So these are some examples of random process. So stochastic processes, or you may say random processes, are widely used as mathematical models of systems and phenomena that appears to vary in a random manner. So a stochastic or random process can be defined as a collection of random variables that is indexed by some mathematical set, meaning that each random variable of stochastic process is uniquely associated with an elements in the set. The set used to index the random variables is called index set. So in this way, random process or a stochastic process are defined. So a random process is a time-varying function that assigns the outcomes of a random experiment to each time instant, xt. When you're talking about random process, and if you compare with random variable, you can say that random process means something is to be very randomly with respect to time, right? For example, that's why the random process is always designated as xt, whereas t is the time. So when random variable vary with respect to time, then that random variable become a random process. For example, if you measure the temperature in a day, and if you start to measure the temperature from 9 a.m. morning to 5 p.m. evening, now from 9 to 5, you measure temperature every 1 hour. So if you take the reading, say at 9 a.m., then second unit 10 a.m., then 11 a.m. up to 5 p.m. So you get a reading of a temperature, and that reading is random. You can't predict in advance that what will be the temperature after 1 hour. So that process comes in the category of random process, because a random variable, which is the measurement of a temperature in a day, is a random variable and its value change with respect to time. That's why we denote this random process as xt. So a random process is a time varying function, right? And if you fix the time, then it becomes a random variable. So random process is a random variable if you fix the time. So when something is to be something, means any random variable is changed with respect to time, then this becomes a random process or a stochastic process. There is also a concept of ensemble, that I will discuss in later slide in this. What is the meaning of ensemble? Now this random process can be a continuous process or maybe a discrete process, right? Like random variable, this random process are also categorized in continuous and discrete. As I said earlier, this real random process are also called as stochastic process. Example is noise. Noise is considered to be a random variable, right? And if you take a noise signal, which is also vary with respect to time, its amplitude change with respect to time, are also come in the category of this random process, or sometimes use a Gaussian process because a noise follow a Gaussian distribution. So that random process are also called as Gaussian random process in case of noise in communication. So noise considered to be a random variable which change its value at every instant of time, and that's why we call it as a Gaussian random process. So if you define random process, you define as a stochastic process is a set of random variables indexed in time. I already give the concept of that. So mathematically, if you compare stochastic processes with probability theory, the term that we used earlier, in probability theory, we have a sample points. We have a sample space. So sample points, here we say a sample function, because that sample function is a function of actually a time. The variable is a function of time. The random variable is a function of time because its value change with respect to time. So sample point becomes sample function in the random process. Sample space becomes ensemble. Ensemble is a collection of all the points, all the sample functions. And random variable become random process, because here everything is to be changed. Whatever the variable that you take in random process is changed randomly with respect to time. So sample point here in the case of random process is a function of time. So that's why we denote, look at this, we denote x as t. X is a random variable with change with time. And this is the time limit, this is the time limit, minus t to t, right? Now, look at the case. Look at this picture. In this particular picture, we have performed 3 experiments, right? And we have performed 3 experiments, or you must say we perform an experiment. And for example, if you consider that as look, we have to measure a temperature, right? We have to measure a temperature in a day, from 9 to 5, right? From 9 to 5. and we perform this experiment in consecutive 3 days, Monday, Tuesday, and Wednesday. So this is the data set that we have on Monday, and that data set is a measurement of temperature with respect to time, and the limit of time is 9 to 5, 9 morning, 5 evening, and we perform this Monday. This is the data set for Monday, this is the data set of Tuesday, and this is the data set of Wednesday. So this is the variation of temperature from 9 to 5 on Monday, and this is the temperature of variation from 9 to 5 on Tuesday, and this is the measurement of temperature from 9 to 5 on Wednesday. So we say that these are the outcomes of the first trial of the experiment, right? And these are the outcomes of the second trial of the experiment, and these are the outcomes of the nth trial. If you take n number of times, you can say nth, but we take this can be assumed as third trial of the experiment, right? So these are the variation. So one thing is clear: the temperature at 10 a.m. on Monday is different from the temperature of 10 a.m. on Tuesday, and the temperature at 10 a.m. on Wednesday, right? So as far as the ensemble is concerned, ensemble is the collection that you have when you fix your time. For example, if you fix your time 11 a.m., right? So the first day. So if you fix the time as, sorry for the interruptions, because there is a a connectivity issue. That's why there is a disconnection frequently. Well, at 11, if you fix the time at 11 a.m. for example, so Monday 11 a.m. you have certain reading of temperature. On Tuesday again you have a temperature. You fix the time as 11 a.m. You again get the temperature, but this temperature is different from the temperature on Monday. And again you repeat this on third day, Wednesday, 11 a.m. What is the temperature? So these all are the reading that is coming when you fix your time, right? So collection of these reading are the ensembles, right? Collection of these are the ensembles. So this is the ensemble. This is the ensemble. Your first reading is x1. X1 denote temperature on Monday at 11 a.m. What is S2? Temperature at second day, that is Tuesday at 11 a.m. And what is SN or S3? It is the temperature on Wednesday at 11 a.m. So when you fix the time and take the samples, then this become ensemble. And if you take the mean of all these readings, all 3 readings or 4 readings or 5 readings, then that become ensemble mean. Is that clear? So ensemble comes when you fix the time, and if you take the mean, that number of reading that you have upon, the reading that you have, if you sum all these, divide the number of reading that you take for the summation, then it becomes a ensemble mean. So random process is also defined as the ensemble collection of time functions together with the probability rule. Now come to the type of stochastic processes, and in that category we have a stationary versus non-stationary process. Both come under stochastic or random process. Well, the stationary process, so stationary process of course are the stochastic process whose joint probability distributions does not change with shift in time, and consequently parameters such as mean and variance if they are present, also do not change over time. What is the meaning of that? Meaning is that stationary process are those type of process where when you shift the time, their characteristics property doesn't change. It remains constant, same. So these type of process are called stationary process. So if a process is divided into a number of time intervals exhibiting same statistical properties, and if you change the time intervals, for example, if our cases measure the temperature from 9 to 5, and if you take the mean, right? Again, you perform the same experiment, but 1 hour delay means 10 to 6. Again, you take the mean of a temperature, both are same. Again, delay 2 hours means start your experiment instead of 9, 11, finish at 7 p.m. Again, you take the mean. So if all these 3 or 2 means are equal, by shifting the time, second time we shift 1 hour times, third time we shift with, so with second time we shift 2 hours. So if their mean or variance is unchanged, means that process are called stationary process. So in a stationary process, everything is to be, their statistical characteristics are unchanged. They are constant. So these are the stationary process. And opposite of that comes the category of non-stationary process, right? Means if a process is divided into a number of time intervals exhibiting different statistical properties, not same. Look at this. Here is the same, here different. Then that process are called non-stationary process. So stationary and non-stationary process are defined in terms of their statistical properties. If you change the time interval, if you shift the time, change the time, if their properties, their statistical properties are same, are come in the category of stationary process, or that random process are called stationary process. And if their statistical property change with your change in time period, time or time scale or time intervals, then it is come in the category. That type of random process are called non-stationary. Now, again we move. Again we have a category as far as the stationary is concerned: strict stationary and weakly stationary. Strict stationary and weakly stationary. Before come to that, before I explain this particular slide, I just give you certain concept. So a stationary process, a stationary process, strict stationary, or you may say strong stationary process, is a stochastic process whose unconditional joint probability distribution does not change with a shift in time. This is the basic definition of strict or a strong stationary process. What is this definition? If you shift the time, then their joint probability or distribution or cumulative distribution function does not change. If you shift the time, then their joint probability are unchanged. Then these processes are called strict or strong stationary process, right? And also parameters such as mean and variance also do not change over time, right? So these are some definition of that. So look at this particular slide. We have a stochastic or random process xt initiated at t is equal to minus infinity is said to be stationary in the strict sense, or strict stationary if, look at this track. Look at this. This is the joint cumulative probability distribution function, and this is another joint probability distribution function with a time shift of tau, right? So xt1, xt2, xtk denotes random variables obtained by sampling process, xt at t1, t2, tk respectively. Then fx t1, x2, xtk, x1, x2 denotes joint distribution of random variables. Now this is one set of joint distribution function of random variable. Look at this version. This version is a shift of time. You have to shift the time, for example, say 1 hour or 2 hours. So this 2 hour or 1 hour is added every time. Right? So this particular denotes the random variables obtained by sampling process xt, t plus tau, t plus tau, t2 plus t tau. So there is a, so we have to add particular time on every time interval, t1, t2, t3, tk plus tau respectively. Where tau is a fixed time shift. So again, we get, look at this, again we have a joint distribution function. So if this joint distribution function, which is come after you shift the time by a factor tau, if this joint distribution function is equal to that one, if the both joint distribution function are equal, then you can declare that this stationary process is strict stationary process. So we already defined this strict. Come to the weakly stationary process. A stochastic process xt is said to be weakly stationary or wide sense stationary if the second order moment satisfies. Number one, the mean of the process xt is constant for all time t, and the autocorrelation function of the process xt depends solely on the difference between any two times at which the process is sampled. So in that way, we have a now come to this topic, ergodic random process or ergodicity. To understand that, the computation of statistical average, that is mean, and autocorrelation function. So here the statistical averages mean that we consider is a mean and autocorrelation function of a random variable. So the computation of a statistical average here. So the computation of statistical averages, sorry, there is a network issue. That's why there is a disconnection of internet regularly. So come to the point. The computation of statistical averages of a random process requires an ensemble of sample functions as a data record that may not always be feasible. So in many real life application, it would be very convenient to calculate the averages from a single data record. This is possible in certain random process called. Now try to understand this, what is ergodicity or ergodic process. We have two things, time average and ensemble function. How you calculate time average? Look at this time average. How you calculate time average? Our example that we take from earlier is the example of a temperature that we measure from 9 to 5 daily, right? So if you measure a temperature from 9 to 5, after 1 hour you take the reading. So first reading come at 9, second come at 10, third 11, and the last come to 5. What you have to do? You have to take the average. Then declare, okay, 20.56 is the average temperature from 9 to 5. So that we call as a time average, right? So what you have to do? You have the reading at different times and you take the mean average. So that become a time average. But how become a assemble mean? Assemble mean. This is assemble mean, this is time average. Assemble mean come in the picture when you fix the time.
Monday 11 a.m. you take the first reading, Tuesday 11 a.m. you take the second reading, and so on, and take the mean. That mean become assemble. So when time average is equal to assemble function, then the process called ergodic process, and this phenomenon is ergodicity, when time average is equal to assemble mean, right? So in this particular slide you see, if these two time average in many random processes, if the time average become assemble function or assemble mean, then you can say that it is a ergodic process, right? So today in this video lecture, when I perform my lecture through video, there is a disconnection frequently. So it's very difficult for me. Every 3 or 4 minutes there is a disconnection. There is an internet issue. But anyway, I just conclude that. So thank you very much.